Okay, y1 vector. You should be familiar with this Cauchy-Schwarz inequality that can be obtained by considering a linear combination of the a and b vector. Here, x is an arbitrary real number that is dimensionless. We assume that a and b are both of the same dimensions. The square of the vector is a scalar product with itself. And if we expand this one, then you will find a square, 2ab, and b squared. They are coefficients of the quadratic form of in a polynomial of x. Because the square of a vector is always a positive definite, in case it's exactly zero vector, only if it is zero vector, it is a equality holds. So according to this inequality, we expect that the discriminant of this quadratic expression must be less than 0 or equal to 0. According to this, we divide this by a factor of 4 and move the second term to the right-hand side, then you will find this expression. This is called the Cauchy-Schwarz inequality. So the immediate consequence is that the scalar product of the two Euclidean vectors is always in the region between the magnitude product of the magnitude of the two vectors. That is this. If we rescale both sides with the a squared and b squared, a squared, b squared, then left-hand side reduces to the square of the scalar product of the two unit vectors. You know the unit vector is defined like that. As a result, this inequality has a solution. The parameterization for this scalar product between two unit vectors is conveniently chosen as cosine theta, where theta is the angle between the two vectors. Special values for this cosine theta is when they are parallel, cosine is 0, cosine 0 is 1, and if they are anti-parallel, then cosine becomes a -1, and if they are perpendicular to each other, cosine becomes a 0. Any vector can be decomposed into two pieces if we bring in a unit vector, arbitrary unit vector. We can find the component parallel to n hat. So x has the parallel component to n hat with the magnitude of scalar product between the n hat and x. A vector parallel to n hat is this. Then if we subtract this part, then you will find the perpendicular component. So x vector subtracted by the parallel component must be the perpendicular component. And these are two vectors, x parallel to n hat, x perpendicular to n hat. If we add these two vectors, we can reproduce this x vector. In addition, they must be perpendicular to each other. Hence, the scalar product between the perpendicular component and the parallel component must be 0. And this is parallel, and this is a perpendicular component. A very important nature of a vector under rotation in 3 dimensions is called Rodriguez formula of 3D finite rotation. We have a vector x, and we have arbitrary axis of rotation n hat. We can choose this one as the z component, z axis of the Cartesian component. In that case, under this rotation, this vector x rotates, transforms into x prime theta, where theta is the angle of the rotation about this axis. We first find the parallel component along the n hat is this, and perpendicular component is this. The parallel component is invariant on the rotation about n hat because n transforms into n hat itself. So it is invariant. It doesn't change at all. However, the perpendicular component relative to the n hat varies. This is just like a rotation of a vector along the x-axis by an angle of theta. Then you will find a new direction. And this new direction is obtained like that. A radius r can be rotated in this way. Then the new component has the x component that is called r cosine theta. And the new component that is perpendicular to x-axis is parallel to y-axis, that is r sine theta. So this is the result. This is a original perpendicular component relative to the original perpendicular component. This original relative perpendicular component rotates like that. So resultant expression for the perpendicular component is this one multiplied by cosine. And another axis, this is assumed to be E1, then E2 hat can be obtained in this way, and E2 hat is actually the E3 cross E1, the cross product. Therefore, the new component generated by this finite rotation about n hat by an angle of theta is n cross x times sine theta. This is general for any finite angle as well as infinitesimally small angle. So please remember this Rodriguez rotation formula in three-dimensional Euclidean space. Cartesian coordinate is a very convenient coordinate system we learned from elementary school. Cartesian is named after this adjective of the Descartes. So the unit basis vector of a Cartesian coordinate system, EI, where I runs from 1, 2, and 3, they are always perpendicular to each other, and their own magnitude is 1. So, for example, E1 dot E1 itself is just magnitude itself, it is 1. However, E1 dot E2, because they are perpendicular to each other, it is a 0. So EI dot EJ hat is always either 1 or 0. And it is 1 only if both of them are the same, 1, 1, 2, 2, and 3, 3. If they are different, we call this a vector index. If the vector indices are different, then it is a 0. We call this one to be the Kronecker delta. And Kronecker delta is actually the ij element of this unit matrix, 3 by 3 unit matrix. They are all 1, and the diagonal component ij equals 1, ij equals 2, ij equals 3. If I and j are different, they are off-diagonal elements, they are all 0. If we make use of Cartesian coordinate system, due to this orthogonality of this base unit basis vectors, computation of a scalar product becomes very, very simple. That is, this scalar product of I and j survives only if both I and j are the same. The computation is greatly reduced into this. That means A11, A1B1 plus A2B2 and A3B3. From this, we can construct a matrix representation of a vector. Usually, we use you have been using this kind of ordered number x comma y comma z, and this is actually the matrix representation of the Euclidean vector. And if we generalize this into a column vector, A1, A2, A3, first, second, third Cartesian components, and B1, B2, B3, and we define the transpose of this column matrix is to be a row matrix. In that case, the product of scalar product A dot B can be represented by a simple multiplication of these two matrices. The product of two matrices are defined in such a way the first, second, and third are being multiplied and added together. Okay, so we can write the scalar product of two vectors in an algebraic form or in a linear algebraic form. And we find that this is a commutative. You can write in this way, and they are identical to each other. They are the same. Once you can compute the scalar product of the two Euclidean vectors, you should be able to compute the cross product of a three-dimensional Euclidean vector. The cross product is perpendicular to the plane on which A and B are placed. When n hat is perpendicular to this plane and parallel to this cross product, that cross product is actually along the direction when we swipe this A to B along an angle that is smaller. There are two ways of rotating, this way or this way. And you notice this one is smaller, this angle is smaller. So when you swipe from A to B with a smaller angle, then your right hand thumb is heading toward the direction of the cross product. So in that case, cross product and the scalar product of n hat should be positive definite. This is the explanation for the small angle. So, okay. This is another important result for the Cartesian unit vectors. E1 cross E2 is E3. We find it is 1, 2, 3 are in order. If you exchange the order, the answer is opposite. Answer is opposite because the definition of a cross product is anti-commutative. While the scalar product is a commutative, you can change the order without changing the value. If you exchange the order of this cross product operation, your final result flips the sign. In addition, if they are the same, it is always vanishing. So these two indices must be different. So the cross product of two Cartesian basis vector is a linear combination of three Cartesian basis vectors, but actually at the end of the day, you will find that is either a zero or parallel to something or anti-parallel to something. For example, 1, 2, 1 cross 2, it is a 3. 2 cross 1 is a minus 3. So if you exchange the order, that is called permutation. You exchange any two numbers in the ordered list 1 to 3, then you will find this new permutation. If the number permutation is an odd number, we call this one to be an odd permutation. Odd permutation, from this, exchange 1 and 2. You exchange a pair only a single time. That is odd number. So we call this odd permutation. From 1 to 3, you exchange this 2, you will obtain this. You have one permutation, and then exchange these 2. Then you will find 2, 3, 1. So you have exchanged twice. Then you can reach an odd, even permutation. In such a manner, permutation, there are 3 factorial permutations. Among 3 factorial permutations, that is 6. 3 permutations are even. That comes from 1 to 3. That is by definition even. And the other 3 permutations are odd, and this one gives this Leibniz tensor, that is a positive 1 and negative 1. If you attach 3 numbers in here, there are 3 times 3 times 3, 27 cases. So among 27 cases, only 6 has a non-zero value. Among them, 3 has a simple +1 value, and 3 cases has -1, and remaining 21 cases, everything else becomes 0. So at the first, if you see this one for the first time, it looks very complicated, but it is actually a very simple calculation. The answer is A cross B is a linear combination of E1, E2, and E3. You find epsilon 1, 2, 3, that is even permutation. 1, 2, 3, then we have positive sign. 1, 3, 2, you have exchanged once, it is odd permutation, so A3, B2 has negative sign on it. In such a manner, 2, 3, 1 is a positive, 2, 1, 3 has negative sign, 3, 1, 2 positive, 3, 2, 1 negative. In a similar manner, you can compute in this way that everything is the same. And this is the actual definition of a determinant of a 3 by 3 matrix. You can put 3 Cartesian basis vectors here and Cartesian components as a row. You can write it in this way as a column. The final result should be the same. Finally, triple scalar product is a very, very important object of geometry. In physics, when we compute the volume of a parallel pipe, we have A and B and C vectors at the edges of this parallel pipe. Volume of this one can be computed in such a manner. If we can make use of this definition, and actually it's not a definition, it's just according to the computation itself, then what we can do in practice is attach the 3 columns, 3 components, Cartesian components of 3 vectors in columns or in rows and compute the determinant. And we know the cross product of itself is always vanishing. It is a very trivial to find that the determinant of a matrix that has two columns parallel, then the final result is 0, directly from the definition of the determinant. Just like the previous case, we can consider the representation that has a row representation that is identical. If you exchange the order from the definition of the cross product, B cross A is the same as A cross B up to sign. Therefore, determinant of a matrix of the order BAC as column, if we exchange these two, ABC, then we have negative sign on it. This is a simple training for determinant calculation, and this is a very important. Triple vector product appears frequently in physics, and this one can be obtained by making use of the application of this Levi-Civita tensor. First of all, the proof of this expression, back cap A cross B cross C, is easy to memorize. A back cap B and C, and coefficient is A dot C and A dot B. Back cap. Remember this expression. And complete proof of this formula is given in Y1. We have Jacobi identity. Jacobi identity is just copy this one. ABC, BCA, CAB, cyclic. However, the sum it looks complicated. Sum is 0. We can make use of this formula for the back cap rule, substitute these results in here, and then exchange A, B, C, A, B, C, B, C, A, C, A, B. That means a B, C, A, C, A, B, A, B, C, C, A, B, C, A, B, C, B, C, A. You find these two the same, they cancel, exactly 0. So middle school students know how to compute the cosine squared theta plus the sine squared theta equals 1, and that appears in physics using vector algebra. A dot B squared is A squared B squared cosine squared. A cross B squared is a sine squared. Aha! If you add these two quantities, then cosine squared sine squared sum is 1. So it is trivial to find that this is true. Using this, A cross B squared can be obtained by subtracting this one by A dot B squared. So it is you can notice it is a sine square equals 1 minus cosine square. And actually this one can be proved by making use of this back cap rule. So you can do it yourself for this calculation. The next part is you should be familiar with the exponential. In physics, we have a sine, cosine, exponential. These three functions appears in physics problem frequently. So you have to remember the definition and how to deal with this expansion and convenient tool of expansion, and it is to be generalized to find the Taylor series expansion of exponential function or any other function. And in here, there are powers. The reason why we have only a 1 over n in the parentheses is that higher order always cancel. you can make use of this expansion tool and taking the limit as n goes to infinity, then you will find that it's an absolutely vanishing contribution. Next, you need to know how to make a differentiation of the sinusoidal function and exponential function from definition that appears so many times in physics problem. And this is a unit radial vector on the xy plane, x-axis, y-axis, angle theta, and this is the unit radial vector whose magnitude is 1, and it has the angle theta with respect to the x-axis and 1/2 of pi minus theta with respect to the y-axis. Partial derivative means there is this variable only and keeping any other variables as constant. That is called the partial derivative. The partial derivative with respect to this angle gives cosine becomes minus sine and sine becomes cosine. That gives the unit vector perpendicular to the radial vector. That is called the unit tangent vector. Unit tangent vector. And you will find that unit radial vector and unit tangent vector, they are perpendicular to each other. And when we consider uniform circular motion, these kind of chain rule must be used to simplify your calculation. And once you can compute the derivative of vectors with respect to angle, then time derivative is quite important to compute the velocity or acceleration in physics. Time derivative is computed by making use of chain rule. First, you take the derivative with respect to theta and take the derivative of theta with respect to angle at the time. Finally, the result is by making use of previous result, we can find that radial vector, unit radial vector has the time derivative that is perpendicular to that vector, and then there is a proportional constant factor that is the angular velocity. In a similar manner, this unit tangent vector's time derivative is perpendicular to its vector, and finally, that is opposite to the unit radial vector. That is the reason why we have a centripetal force that is toward the center of a circle. In a similar manner, double time derivative can be computed sequentially.